Okay, so welcome back. We will be discussing on the properties of monosaccharides. Important properties of monosaccharides can be listed as isomerism, its reducing power, mutual rotation, glycosidation. I hope you know what is isomerism. That is, if two molecules having same molecular formula exist in two different molecular structures, you can say they are isomeric, isn't it? Specifically, when we speak over here, stereoisomerism we are speaking about. Stereoisomerism is all about the spatial arrangement. Okay, so stereoisomers, spatial arrangement. So we have already seen that a monosaccharide, they have a carbon chain, right? A chain of carbon atoms, and to this main chain of carbon atoms are attached hydroxyl groups, hydrogen groups. Then, like one of the carbon in the particular carbon chain exists in the form of aldehyde or ketone. These are the basic structural features of a monosaccharide. Depending upon the number of carbons, the monosaccharides may vary, right? And we already saw that except for the carbonyl carbon and the carbon at the other extreme end, all the carbons in the chain, they are asymmetric, right? That is, except two carbons, the rest of the carbons in the carbon chain of any monosaccharide, they are asymmetric, especially in the case of aldohexoses. In ketohexoses, it is one less than the number of carbon, number of carbons in aldohexoses. Okay. If there are three carbons in a carbon chain, in the case of aldohexoses, one among them it is asymmetric carbon. In ketohexoses, there are no asymmetric carbons. In the case of tetroses, that is with four carbon atoms in the chain, two carbons in them are asymmetric, while in the case of tetroses, it is there is only one asymmetric carbon. Okay, so that is how it is. Okay, and due to the presence of what is asymmetric? Asymmetric carbon, it is otherwise referred as a chiral center or chiral carbon. It is a carbon atom with four different substituent groups. Okay, it is otherwise referred as asymmetric. Okay, so it is a chiral carbon. And due to the presence of the chiral carbon, we see there is what we call stereoisomerism. Okay, stereoisomerism, that is isomers, stereoisomers, they are molecules with the same chemical bonds and same chemical formula, but different configuration. That is the spatial arrangement of atoms. That is slightly different. Okay, we can see with an example over here. So these are the stereoisomers. What happens over here? Here what happens is CHO, you can see it is the same, CH2OH is also the same. But there is a difference in the spatial arrangement of the OH group with respect to the main carbon chain. Okay, one is on the right side and the other in the left side. Okay, so it results in the two different isomers. Okay, so we have two D isomer and we have L isomer. Okay, so that is about the stereoisomers, where the spatial arrangement of the substituent molecules differ. But basically the molecular formula it is the same. Here also it is C3H6O3. Here also it is C3H6O3. Right? So we have two stereoisomers. Now there are two kinds of stereoisomers. One is enantiomers and the other is diastereomers. Sorry. Enantiomers, they are stereoisomers that are mirror images of each other. So what is mirror image? Here you can see there is a mirror plane over here. This is one molecule where you can see this is the carbon atom having the different constituents, right? The constituents attached to the carbon, hydroxyl, hydrogen, CHO, the CH2OH. So this is glyceraldehyde. Okay. Now what happens in the mirror image? Hydroxyl is on this side. Okay, which side? It's on the left side. While in this particular pattern, hydroxyl is on the right side. Okay, so there is a shift. The position of CHO and CH2OH remains the same. It is above the plane, below the plane, but the hydroxyl group and the hydrogen attached to this particular carbon, the position interchangeable. Okay, and in this particular case, the isomerism, it is enantiomer, because the two stereoisomers are mirror images to each other. What about diastereomers? Diastereomers are pairs of stereoisomers that are not mirror images of each other. And this happens mainly when there are more than one asymmetric carbon or more than one chiral carbon in the molecule. Okay, This is with the case of glyceraldehyde, where this is the only what you call asymmetric carbon. Okay, so in the case of the monosaccharides with only one asymmetric carbon, this is possible. Stereoisomerism is possible. Okay, or what we call as this is enantiomer. But always it needn't be the same. When stereoisomers are not mirror images of each other, we call that as a diastereomer, and diastereomer arises whenever there are more than one asymmetric carbon in the molecule. Okay, we'll see it in detail. Now, all carbohydrates contain at least one asymmetric carbon or the chiral carbon, and they are hence optically active, or they exist in isomeric form. In addition, carbohydrates can exist in either of the two conformations, as decided by the orientation of hydroxyl group about the asymmetric carbon farthest from the carbonyl carbon. This we have already seen. That is, this is the carbonyl carbon. Okay, we'll see. 1 minute. Okay, so here we saw this is the carbonyl carbon. Okay, and depending upon the orientation of hydroxyl group on the asymmetric carbon farthest from the carbonyl carbon, it determines whether it is D or L form. Okay, that is the configuration, D configuration or L configuration. I hope it is clear. Okay, so it is said that carbohydrates can exist in either of the two conformations. What are the two conformations? D conformation and L conformation. And how it is decided? It is decided by the orientation of the hydroxyl group on the asymmetric carbon farthest from the carbonyl group. Okay, I hope it is clear. Okay, now with a few exceptions, those carbohydrates that are physiologically significant exist in D conformation. Okay, so actually what does it mean is all the biologically important sugars or monosaccharides, they are in D conformation. So D isomers or D monosaccharides are the biologically active molecules. They take part in the formation of oligosaccharides and polysaccharides. Okay. Now, as we have already mentioned, enantiomers are stereoisomers that are exact mirror image of each other. Okay. Now, number of stereoisomers. Okay. If we have a molecule, and we can say that number of stereoisomers depends upon the number of chiral carbon in that particular chain. Okay, so we can get number of stereoisomers of a molecule by finding out 2 raised to n, where n is the number of chiral carbon. Okay, so if it is having only one chiral carbon, the number of isomers will be 2 raised to 1. That gives 2. Right? Glyceraldehyde, there is only one. This is the only one chiral carbon, isn't it? So we have 2 raised to 1, that is 2. D-glyceraldehyde and N-glyceraldehyde are the two conformations or two stereoisomers. Depending upon the number of asymmetric carbon, we can have as many number of stereoisomers from this particular form. Okay, 2 raised to n. I hope it is clear. Okay. Now, coming to diastereomers, we already mentioned that is monosaccharides that are made up of more than 3 carbon atoms have multiple asymmetric carbons, that is more than one asymmetric carbons. So they exist not only as enantiomers but also as diastereomers. Okay, so isomers that are not mirror image of each other, that is a diastereomers. Typical example, D-glucose and D-galactose. If there was a mirror plate over here, and we need to find the isomeric form or the mirror image of the D-glucose, how it will be? It will be CHO, OHCH, HCOH, OHCH, OHCH and CH2OH. That will be the conformation, isn't it? That means on the what all components or what all constituents are on the right side of this particular glucose, that is D-glucose, it would have been on the left side in the case of mirror image, isn't it? But when we compare D-glucose and D-galactose, we can see that they are isomers because they have the same molecular formula C6H12O6, but they don't have the same the constituents are not arranged in the same pattern. What is the difference? You can see on the fourth carbon OH, the hydroxyl group is on the left side in case of D-galactose, while it is on the right side in the case of D-glucose. So they are isomers because they have structurally different molecular pattern. Okay, molecular arrangement is different, but molecular formula is the same. So they are isomers. but they are not enantiomers because they are not mirror images. So this kind of a stereoisomer is referred as a diastereomers or diastereoisomers. I hope it is okay. Okay. One example is D-glucose and D-galactose. Another example we can find is D-glucose and D-mannose. Okay. So we have found what is isomerism, stereoisomerism, enantiomerism, diastereomerism. Okay. Now passing on to the next property, that is reducing ability. Okay. What is reducing ability? That is, they can reduce some other molecule. Okay. When we say that monosaccharides have the ability to reduce some other molecule, what happens is you can see, yeah, okay. So this molecule, it is D-glucose. Okay, it is D-glucose. You can see how it is D because this is the carbon, which is asymmetric carbon farthest from the carbonyl carbon, isn't it? And here the hydroxyl group is on the right side. So this is D-glucose. How can we be sure that it is a glucose molecule? Because the third carbon is the only one with hydroxyl group on the left side. So it is glucose. And it is D-glucose because hydroxyl group on the penultimate carbon, it is on the side. Okay, so it is D-glucose. Fine. Now what happens when it is getting reduced? No, it reduces another molecule. Okay. When this molecule, it reduces some other molecule, this gets oxidized. Okay. When we say that this molecule is having reducing power, what does it mean? This molecule can reduce some other molecule. Okay. Here the molecule is Cu2+. Okay. It is Cu2+. Cu2+ means Cu copper containing molecule. Okay. Cupric containing. Okay. So what happens here? This molecule, that is D-glucose, reduces Cu2+. Okay. What happens as a result? Cu2+ get reduced while the glucose get oxidized. Okay. Where is it getting oxidized? It is getting oxidized at this position. Okay. And what happens as a result? Instead of CHO, it becomes COOH. Clear? It is getting oxidized. Fine. So, it is a redox reaction. So, what is reducing ability? Reducing ability or reducing power of monosaccharides means these monosaccharides, it gets oxidized while reducing some other molecule. Okay. Usually they oxidize mild oxidizing agents like cupric ion or cupric ion containing compounds. Okay. Monosaccharides can be oxidized by relatively mild oxidizing agents such as cupric ion. Okay. The carbonyl carbon is the one oxidized to carbonyl carbon is the one which gets oxidized to the carboxyl group. Okay, that is what happens during the particular redox reaction. Glucose and other sugars capable of reducing cupric ion are called reducing sugars. Okay, these are known as reducing sugars, which can reduce cupric ion to cuprous. This is cuprous. Fine. During this process, you can see that the oxidation happens at CHO. Okay, it gets an oxygen molecule, it's an oxygen atom. So it becomes this is the part where the oxidation is happening. So you can say that only those monosaccharides with the CHO group can be oxidized or can act as reducing sugar. Okay, so cupric ion oxidizes glucose and certain other sugars to a complex mixture of carboxylic acids, and this is the basis of Felling's reaction. Okay, so Felling's reaction or Felling's test, it is where we test the presence of glucose or reducing sugars in a sample solution. Okay, so if we have a sample solution and if we need to find whether the monosaccharide is present or absent, we can, if we add Felling solutions and if we mix it and slightly boil it, we can see there is a color change. Okay, what is the color of cupric? Copper sulfate, CuSO4. What is the blue color? Isn't it? It is blue color, right? When it gets reduced, what happens? It may give a brick red color, okay, or a red color. So there is a shift from blue to red, right? And this indicates that cupric, it is getting reduced to cuprous, fine. And this particular reaction is used to indicate the presence of reducing sugars. Okay, that is those sugars which is having a free aldehyde group. A free aldehyde group is a must for having the reducing ability. Fine. So this is regarding the reducing ability. So we saw isomerism as well as reducing ability of monosaccharides in this presentation. Okay, we'll continue.